Hello. Good morning, everyone. So my name is Tolentino. I'm from the University of the Philippines, and together with my co-author, Dr. Marc Talampas, I'm here to present the design, development, and evaluation of self-powered GPS tracking system for vehicle security. So I have a lot of slides to show you, so I would just go ahead and breeze through each of them. So the purpose of this study is to harvest vibration energy from a test vehicle and actually use the harvested energy in order to track the vehicle location. So for this study, we used a test vehicle and we acquired its vibration profile. So we used tri-axis accelerometers and placed it in 4 different locations as shown in the figure. And the results show that the most abundant source of vibration energy is the back axle. So in this slide, the top figure shows the vibration profile of the rear axle in the z-axis direction, which has a mean vibration magnitude of 0.98 G, and the bottom graph tells us the frequency spectrum and the power spectrum. Now from the frequency spectrum, the green plot, there are 3 major peaks occurring at 61 Hz, 85 Hz, and 120 Hz. And from the power spectrum, we could see that the 61 Hz frequency offers us with the greatest amount of energy. And we use this frequency in the tuning of our piezoelectric generators. So we used V20W piezoelectric generators as shown in the figure to your left, and we configured them in cantilever beam configurations. And we used tuning masses to actually tune this piezoelectric generator to the desired frequency. So shown in the figure to your right is an electrical model for this piezoelectric generator. So this model is actually used as a part of a voltage doubler circuit. So this voltage doubler circuit acts as a rectifier to rectify the waveforms from the piezoelectric generator. So here are the waveforms of the output of the voltage doubler circuit. Waveform A is the open circuit voltage, and waveform B is actually when you attach a load to the output. Waveform B is the waveform. So as you notice, as you increase the load, the peak-to-peak voltage of the waveform decreases as well as its duty cycle. So this property is very important to us since since the harvester is based on this property. So if you harvest too much energy, this duty cycle increases dramatically, and when you harvest too less, this duty cycle increases. So you have to harvest somewhere in between in order to operate at maximum power point. So we used 3 of those piezoelectric generators shown in this slide, and we configured them in a radial topology. So we tuned each and every piezoelectric generator to 61 Hz to suit the application. And here is a load profile of the piezoelectric generators. So we used a constant voltage load as our load, and we varied the load from nearly 0 up to the open circuit voltage. The open circuit voltage reached about 60 volts. So noticeable in the graph is the clippings in the right hand side. This represents the reverse voltage breakdown of the diodes used for the voltage doubler circuit. What's important in this graph is that the maximum power is harvested at 30 volts, which is uh, half the open circuit peak-to-peak voltage. So those concepts are used in the harvester. So this is a schematic diagram of our vibration energy harvester. It's composed of a voltage doubler circuit, the buck converter, as well as the controller, which is composed of three comparator stages. So the goal of this harvester is to switch the buck converter such that the peak-to-peak voltage waveform of the harvesters or the piezoelectric generators is 1/2 the open circuit voltage in order to get the maximum power point, and to generate a pulse train that would drive the switching converter and use the piezoelectric generator waveforms without perturb and observe methods, meaning without temporarily disconnecting the piezoelectric generators from the harvester in order to generate the pulse train. So here's a photo of the prototype of our harvester as well as the inductor used for the buck converter. So we characterize the harvester in terms of its output power, efficiency, and adaptability to varying vibration magnitudes and vibration frequency. So the harvester consumes a maximum of 200 microwatts, and we harvested maximum of 19.8 milliwatts with a vibration magnitude of 0.98 G. So its efficiency reached about 71%. So here's the characterization of the harvester in terms of varying vibration magnitude. So with a window of plus minus 30% deviation from the nominal vibration magnitude, we were able to operate within 1% of the maximum power point. Also, with plus minus 1 hertz deviation from the nominal vibration frequency, we were able to operate within 6% of the maximum power point. So for the storage unit, we used a two-tank energy storage unit as proposed by Junpan et al. So it's composed of a primary storage, which is a lithium-ion battery, and a secondary storage, which is a 1 farad supercapacitor. So the purpose of this storage unit is for fast system startup and operation. So the secondary storage unit charges up first and provides power to the harvester even if the primary storage is fully depleted. So what happens is the secondary storage is charged first and it powers up the harvester, and it continues to be charged, and when it's fully charged it transfers its energy to the primary storage unit. So this cycle repeats until the primary storage is fully charged. Okay, so we characterize this storage unit in terms of its charge time. So with the 19.8 milliwatts coming from the harvester, we were able to charge the 1 farad supercapacitor to around 12 minutes, from 2.5 volts to 5.5 volts. And the primary storage takes much longer to charge. It takes about 60 hours to charge from fully depleted state to its nominal state, which is 3.7 volts, and 200 hours for it to fully charge. Okay, for the tracking unit, we used a micro mini GPS receiver with an embedded chip antenna and an ADH 8066 GSM module. So the purpose of this experiment is to test whether or not we could get actually the vehicle location when you place this tracking unit in the rear axle of the vehicle. So we used the GPS and GSM modules powered directly by our primary storage and a microcontroller which controls this module. So even with a bad weather, actually a stormy weather, we were able to track the vehicle location when the tracking unit is placed in the rear axle of the vehicle. So this map is actually the map of the Philippines. So the vehicle traveled an 85-kilometer route towards the destination. Okay, so we integrated all the parts together. So shown in this slide is a system block diagram. From left to right, we have the piezoelectric generators, the rectifiers, the energy harvesters, the two-tank energy storage unit, the tracking unit, and the microcontroller which controls all these peripherals. Okay, so this system, the initial design was to construct two modes of operation, the normal mode and the continuous tracking mode. So the actual purpose of this experiment is to protect the vehicle, because when the vehicle is stolen and its primary storage or its primary source of energy, the car battery, is sabotaged, you have no means of tracking the system. Your last line of defense would be a self-powered tracking system. So we devised two modes of operation, the normal mode and the continuous tracking mode. In the normal mode, you send twice the vehicle location during the start and end of the vehicle journey. So in the continuous tracking mode, on the other hand, transmits information every 30 seconds. So the system enters continuous tracking mode when it receives a keyword from the user telling it to go into continuous tracking mode. So in order to perform these modes, we implemented system states, so shown in this figure. So I will not have time to explain in detail each state. So but the purpose of this state, what it provides us is we were able to predict the dwell time and the energy consumption from these system states, and from that we were able to have a study actually a sustainability study for the system. So looking at the available energy, our primary storage offers us with 1.45 kilojoules of energy, considering our 3.7 volt lithium-ion battery, 860 milliampere hours. And in addition to that, we have our vibration energy coming from our harvester, which harvests 19.8 milliwatts with the nominal vibration of the vehicle. So in normal mode, we consume 114 joules of energy during the start and another 114 joules during the end of the vehicle journey in order to transmit data. So in order for our system to become sustainable, meaning in order to replenish the energy expended in each transmission, we need about at least 3.21 hours of uh, of vehicle travel. So for the continuous tracking mode, the system will never be sustainable since the energy expended by the loads is too great. But we will be able to transmit 2,174 times for a period of 3.6 hours before fully depleting the primary storage. And with this time, I think we will be able to track the vehicle in case it's stolen. And after the continuous tracking mode, the system enters again normal mode in order to replenish its lost energy. So that concludes my presentation. So uh, thank you for listening.
I would have a question. Your frequency of 61 hertz,
Yes.
how stable is this frequency? I could imagine when the frequency changes, the energy harvester goes out of resonance and the energy declines.
Actually, the 61 hertz, we had another study which shows that the 61 hertz, actually the resonant frequency of the vehicle, changes together with the RPM of the engine. So actually, this resonant frequency is relevant to the driver of how he drives. So for in this case, the driver is me. So I'm a typical driver, I think. So we use this 61 hertz for the harvester.
More questions?
Yes.
May I ask why you choose such a bulky inductor in your bucket lab? I read something like 10 milliampere.
Yes. Actually included in this study, not shown in this slide, is we experimented on different inductor values, and the study shows that as we increase at some point, as we increase the inductor value, the efficiency increases, and when you increase it further, the efficiency drops. So from that study, the one giving us the 71% efficiency, which is the highest frequency which we achieved, was the 10 milli Henry's inductor. So it's bulky, but this is a prototype work in progress. Is my answer okay?
Are there more questions? Thank you.
Okay.